Boa tarde a todos que estão presentes aqui, o pessoal que está assistindo no YouTube. É uma honra aqui apresentar o nosso palestrante convidado, o Dr. Jacob Forschel. Jacob é pesquisador de pós-doutorado na Universidade de Berna, Suíça. Ele defendeu sua graduação e seu mestrado na Universidade de Oxford, Inglaterra, e seu doutorado em Calgary, no Canadá. Então o Jacob vai falar um pouco sobre o papel da especiação do ferro 3, ferro ferroso e ferro férrico em minerais e em rochas metapelíticas. So Jacob, you're welcome. Have a good presentation. After we can open it to questions and commentaries.
Great.
Thank you very much.
Thank you for that introduction, Lucas, and hi everyone in the room and everybody online. Today I'll talk about ferric and ferrous iron and metapelitic rocks and minerals and metapelitic rocks more broadly. It's great to be here in Brazil. Thank you for having me. Before I start, I should probably acknowledge a couple of people. These are my Masters and PhD supervisors, Dave Waters on the left and Dave Patterson, who've acted as a continuous sounding board for my ideas over the last 5-6 years. And I don't think this work would be anywhere near as well complete as it is without them, so I should mention that first. But I always like to start kind of broad and think about why do we care about pelites, these shales and mudstones in the crust, and I rationalize it in two ways. The first is that they're really abundant in the geological record, and so this is a graph of the age of the Earth in million years along the bottom against the volume percent of sedimentary rock, and pelites form 10 to 40% of the rock throughout time. And so that means that when we have some kind of continental collision, they're inevitably going to be involved in it, and we can go back and use them to study the origins of the past. And the second reason they're really useful is that, well, they have mineral assemblages that are particularly sensitive to changes in pressure and temperature conditions within these origins. And so I put up a schematic pressure temperature diagram here to show all of the different assemblages that exist. This is in the amphibolite facies for metapelitic rocks. But there's a caveat with this, and that's that this diagram is for a kind of an average pelite or shale, if you will, that has a specific amount of each of these different major element components. And there's really a third hidden axis here that's bulk composition. And that if you start to change the amounts of these major elements, these fields of stability for the mineral assemblages shift. And we need to understand how much that might shift so we can compare pelites between different orogenic belts across the world. The other reason pelites are great is that, as with all metamorphic rocks that we're interested in, they have mineral compositions that are sensitive to changes in pressure and temperature. And I put up this diagram here of the relationship of chlorite to GON and the iron-magnesium ratio within them. This is from Hans Ramberg's original paper on thermobarimetry. But this ratio that we use between iron and magnesium is between the magnesium and the iron 2+ in most cases. And well, there's two main valence types of iron in rocks. There's ferric iron, or Fe3+, or Fe2O3, and there's ferrous iron, which is Fe2+. And so understanding the relationship between these two helps us understand the pressure temperature conditions that we infer from thermobarimetry. So they're kind of the two things that I've tried to attack as part of my work, and the two main things I'm going to talk about today. So the first is, what is the major element geochemical variation in pelites? How much variation is there? Is it appropriate to have an average pelite? And secondly, what's the amount of iron 2 and 3 in common metapelitic minerals? So we'll start with this for the first part of the talk. So this started about 2.5 years ago. I was out in the field with Dave Patterson, my supervisor, looking at some rocks in the beautiful Canadian Cordillera, and I asked him this question: what is an average pelite? Because I wanted to make a phase diagram for an average pelite that we could compare across the world. And he said, well, in the past I've used the composition I've shown on the left hand side here. This is from the Nelson oil in Canada, and this is a PT diagram that's a bit wonky here, but similar to the one I showed earlier, have with this composition. And I said, okay, well, what about other people? Other people use different compositions to make diagrams for an average or typical P-light. And he pointed me towards a paper by Doug Tinkham, a classic paper on politic phase equilibria. And he uses this composition that's slightly different from John Ferry's 1982 work. And he also, in that paper, makes some TXAL diagrams. And so he shows the importance of the amount of aluminium on the mineral assemblages, particularly at lower temperatures, and how that will change not only the assemblage, but the compositions and the modal abundances. And that's anyone who has done basic metamorphic metrology will have come across an AFM diagram like this. And this is from Frank Spear's Big Blue Bible textbook. And he has these fields for high ALP lights and low ALP lights. And this left me with a conundrum of, do I make an average diagram for a high ALP light or a low ALP light? What's the distribution of high AL to low AL across the world? Or do we have more low aluminium P lights or more high aluminium P lights? So I had this question. I then had this question that both of these compositions use FeO total. They just consider all iron as iron 2+. There are compositions out there where people have measured iron 2 to iron 3 with this 2 main valence states of iron in rocks, and I'll talk consistently through this talk about the following variable that's X Fe3+. And so when I say that, I mean the amount of iron 3 over the total iron. That's all you need to take home from that in moles. And so here's a composition from J. Ague's 1991 paper. This was used in a recent phase diagram modeling paper that presented new solution models by Dick White. And it has an X-Fe3+ of 0.25, so 25% of the iron in the rock is supposedly iron 3+. They fudged the value in this diagram on the right, actually. But that again left me questioning, how much iron 3+ should you be assuming is in a typical P-light? And if you compare that to some of the other averages that have been published over the years, this is Shaw's 1956, a fantastic paper from a long time ago where he has an average X-Fe3+ of 0.28. Atherton and Brotherton, a classic work in the Dalradian, 0.32. And if you look across this table, you notice that there's subtle differences between all of these supposedly average values for what a shale is. If it's in the titanium that goes from 0.8 to 1.2, or the manganese from 0.08 to 0.2, and that all makes a difference when we're looking at these diagrams on the right hand side and plotting where the lines are. And I just wanted to quantify that, how much exists. The last kind of big issue I had is that this paper on the right uses J. Ague's 1991 payload, but if you go and if you go and read that paper, Jay clearly defines an average shale and slate, an average green schist facies rock, and an average amphibolite facies rock. And he shows, as you would expect with metamorphism, that there's devolatilization and we lose volatiles with increasing temperature. But at the same time, the main point of his paper is that silicon also decreases and titanium and aluminium increase, i.e. that there is mass transfer and mass change during metamorphism or metasomatism. And that is kind of, we have this underlying fundamental assumption when we make a phase diagram like that on the right hand side, that it has a constant composition. So if we're removing elements as we increase pressure and temperature, then we have to reconsider how appropriate it is to model with a closed system. And so I also had this question of, is mass transfer significant? So from this top question, I found myself 3 more questions, which were, what's the distribution of low to high ALP lights? What's the proportion of iron in what proportion of iron in P lights is iron 3+? And is metamorphism of P lights and metamorphism in general an isochemical process? And so I went to answer those, and the way to do that, in my opinion, or one way, was to make an extensive literature compilation and take all of the geochemical data I could find and analyze it together. And so I spent a long time during COVID searching through Google Scholar, ProQuest, which is a big thesis repository, as well as university thesis repositories. All this data that was kind of dead and hadn't been looked at in the back of people's theses or in papers that I found on this Hathi Trust that hadn't been scanned or had only just been scanned but hadn't been used by people. And I extracted all that data to make one humongous Excel file and then use that to look at and try and answer these questions. And so I ended up with, after some culls, 5,729 P-lights from 103 regions. It's 20 times bigger than any other previous database of P-lights, I think. And these are where they all are. The bigger the circle, the larger the number of studies. So lots from the Cordillera, lots from the Acadian in eastern North America, the Dalradian, the Alps, Himalayas, and then the Ryoki and the San Bagua belts in Japan are the biggest areas. Brazil's lacking here actually, which I should talk to some people here to increase the size of that in my database. And I use that to answer these questions. So what's the distribution of low to high LOP lights? Well, here is the same AFM diagram I showed you before, all 5,000 analyses that I could plotted, and they're colored according to a probability density estimate. So you can see here, there's no split between low and high ALP lights, it's just a band that runs through. And I can tell you that the worldwide median of all of these analyses sits at the star. That's around about 0.18 A in terms of the aluminium content and 0.42 XMG. And 50% lie within this, so between 0 and 0.4 XMA and between 0.3 and 0.55. So this kind of tells us two things. Yes, lots of P-lights in terms of AFM probably have a very similar composition, and for us to compare a P-light in the Alps to a P-light in the Cordillera is probably okay, but there are a lot of P-lights that sit outside this range of composition that will give very different assemblages, modal abundances, and compositions of minerals, and so we should be aware of that, I think. Okay, so that's question one answered. What proportion of the iron in P-lights is iron 3+? The issue with this diagram is that I have just FeO total. I've lumped it all together here, and I want to look at the ratio of iron 3 to the total iron, which is XFe3+, and I plotted both of these variables here. So on the left is XFe3+ on the y-axis, and on the bottom is XMG star, and I called it star because it is simply the iron 2+, not the iron total. And so there were around about 2,000 rocks in the database where someone had done a titration to determine the amount of FeO or Mossbauer, and we use those to look at the spread in XFe3+, and the majority of P-lights lie between 10 and 30% of the iron, according to these analyses, is iron 3+, but there's a wide spread, everything from 0 all the way to 1, and also a spread in XMG. Okay, my last question is the metamorphism of P-lights an isochemical process. What do I mean about this? It's the devolatilization. So does the abundance of these major elements change with increasing grade? So as we go from a shale to a phyllite to a schist to a migmatitic gneiss, do we lose elements? So I took all 5,000 analyses and I put them into one of these 9 categories. This is a PT diagram here, and they were either diagenetic, Anki zone, chlorite zone, biotite zone, etc. upwards. And they're meant to be zones of broadly increasing temperature based on the assemblage that was in the rock reported by the authors. And I looked at the concentrations in the elements. So this is my 9 categories across here. The first graph, these show the dots are the mean, the boxes are the interquartile range, and the lines represent the median. And so LOI consistently decreases across the entire spectrum, which is great to see. That's what we expect with devolatilization. And the XFe3+ that I was talking about before, that decreases until the biotite or garnet zone, and then seems to be somewhat constant, perhaps at higher grades. We'll come back to that in a second. And so I retook the database, I minused the LOI out, I converted all the iron to FeO for fairness, and then I examined all of the other major elements to see is there any change in those with grade after you've taken account for the fact that because percentage of some data, I can't compare a shale with 8 weight % LOI to a migmatitic gneiss that has 1 weight % LOI. So I renormalized everything. And here's a couple of those graphs to show what we found. This is potassium content. There's some variation perhaps slightly, but overall I think within the uncertainty on these interquartile ranges, it's pretty flat. It's not continuously increasing or decreasing with the LOI change that we observe. And so I would say, yeah, little consistent variation with grade. And the small changes that we observe, are they metasomatism in terms of what Jay Agu was pointing out, or are they sampling bias? Well, I think the manganese here shows this clearly. The highest manganese value is in the garnet zone, of course, because everybody, when you go to the garnet zone, is trying to find garnet, and in the zones above that, they also all contain garnet. And so I think what we have is just there's some slight bias in all of these analyses that people have taken. And so I'll then just move quickly to look at XFE3 plus here. So one thing is that obviously this is a ratio that varies from 0 to 1. And a lot of these bars are quite large. If you look at the Yankee zone, you know, the interquartile range is between 0.2 and 0.8. So there's a wide spread in the XFE3 plus values at a single grade. And so we examined that in a little bit more detail. Here's that same graph, but just with the pictures to illustrate it. And what you observe if you go and read the literature is that there's variation in XFE3 plus at all metamorphic grades. So we have red versus green shales that's interpreted to be differences in perhaps iron 2, iron 3 content and organic matter. This is a paper where they look at the centimeter scale of thin sections. They have hematite-rich bands versus ilmenite-rich bands that show the difference in the oxidation state. This is a classic study by a bloke called Graham Chinner from the Barrovian zones. He has meter-scale bands of hematite-bearing versus ilmenite-bearing peelites. And then even all the way up into the granulite facies. This is some rocks from Madagascar from Stephen Boger's work. He has entire formations that have magnetite versus next door ones that are ilmenite bearing that show very different ratios. And so what I tried to do is, instead of classifying by grade, where there may be this overall decrease in low metamorphic or diagenetic to low metamorphic grades, I classified where I could do according to the type of oxide that was present in the rock. And so this is the same diagram, just expanded. And I took each analysis, I looked at what the opaque oxide was according to the authors, and I have a group for no iron oxide, a group for ilmenite, a group for magnetite, and a group for hematite. And we see actually that I expected there to be a continuous increase, but the means, which are the dots here, are similar for the bottom three, but much higher in the hematite-bearing rocks. So if you have hematite in these typical peelites, you'll probably have an XFE3 plus that is much higher. And so there's variation at each of the individual grades, as well as perhaps a general decrease in XFE3 plus at lower grades. Okay, so did I answer my 3 questions? Well, I think there's no clear separation between low and high ALP lights, as might be inferred based on that diagram from Frank's book. 10 to 30% of the iron is iron 3 plus according to those analyses, and I think the differences that are present probably represent sampling bias, and so it is somewhat justifiable to look at a P-light across the entire grade. So what is an average P-light? Well, we just published this table that has the worldwide median P-light in it, alongside median P-lights from all of the different regions throughout the world, all those big areas that I found. And so if you want to look at this database and compare how your P-light looks to what we have worldwide, it's freely available online, and so anyone can go and look at that to see where your spot's relative. So that was my first question, and I'll take a break there for a second. My second question was, what's the amount of iron 2 and iron 3 in these common politic minerals that affects what we're doing in terms of thermobarimetry? So for a bit more background on this, as I'm sure most people here know, we use EPMA data commonly to do thermobarimetry. So we go to the probe, we decide we're going to analyze this biotite here and come out with a weight percent analysis that looks something like this. And we perhaps combine this with some analyses of other minerals in order to come up with a pressure temperature point on a diagram like this. But as we said earlier, there's 2 valence states of iron. And so how much of this FeO is Fe3 plus and how much is Fe2 plus? And that matters for this ratio of magnesium to iron. And so you can estimate iron 3 plus by charge balancing in minerals like garnet and pyroxene, oxides, and amphibole, if you believe it. But you can't do that in biotite, chlorite, muscovite, staurolite, all these politic minerals that are really important for us in P-lights. And so what do? Well, you can measure iron 3 plus in these minerals, and people do, and there are many techniques. You can use microzanes analysis, but that requires a synchrotron. You can use XPS or EELs, but these are either very awkward in terms of the sample prep, not widely used, or they require TEM time. And then there's perhaps the 2 most classic, which is that you can do Mossbauer spectroscopy, which again either requires a synchrotron or bulk analysis, which is even harder now because the sources they need for the Mossbauer all come out of Ukraine, so nobody is doing lab-based Mossbauer at the minute. And then there's wet chemical analysis, which is the classical way to do it. But again, both of these are bulks techniques, they're not in situ. So you have to take your rock, separate out all of the biotites, hope that they're not that altered, and look for the iron 2, iron 3 ratio. So not ideal, but better than nothing, but probably not something that most researchers are going to use. And so we want these kind of, what I'd argue is we want an estimate of iron 3+, because we're now using these very advanced phase equilibrium models. This paper that I showed before, they added iron 3+ N members for, well, biotite, chlorite, muscovite, staurolite that I think are, well, not that well constrained. And if you're going to use these models, you have to have an idea of how much iron 3+ is in your minerals to get a good idea of the XMG. So to take advantage of them, we need iron 2, iron 3 in your bulk, which I talked about earlier, but also iron 2, iron 3 in the politic minerals. So I wanted to answer a few more questions here about this. First one was, well, what's the XFeD+ on average in biotite, muscovite, chlorite, and staurolite? Do we have an idea of how much it should be? Can I just put in a general estimate to take out some iron 3+ for my biotite before I do my thermometry? Does the XFeD+ in those minerals vary systematically with PT and X? Is there a way for me to figure that out? And then if I can get those two, how well do the recent models reproduce the XFeD+ in these minerals? Are they doing a good job? And so to answer the first one, we just did the same thing again. If you go back and read all of the literature from the late 50s, 60s, and early 70s, before the probe had really taken hold, everybody was doing wet chemistry. And there's far more wet chemistry out there than you might think. And it's not perfect because it's bulk, but it at least gives us an idea of what we've done so far, what we can understand, and I decided to collate that all together to give us a basis for what we know. And so there's 77 studies classified into 47 regions. Essentially, the bottom 4 numbers are what you need to worry about. I have in P-lights 500 analyses of iron 2, iron 3 in biotites, nearly 200 in white micas, and then far fewer in chlorites and staurolites. And if you just take the average of those analyses, I come up with this table on the right-hand side. The uncertainties are quite large here, but the XFeD+, biotite is about 10% of the iron is iron 3+, white mica is more than 50%, chloride and staurolite are less than 10%, much lower. But we also need to pay attention to this right-hand column because XFeD+ doesn't tell the whole story. Biotite has far more iron in total than muscovite. And so biotite has, even though it probably has 28% iron, it has on average 0.17 iron 3+ cations. But white mica has a very small amount of iron, but lots of that iron is iron 3+. And so white mica takes up 0.28 cations of iron 3+. So there's probably quite a bit of iron 3+ sitting in your muscovite in your rock, in your standard P-light. And so I then wanted to try and answer that second question to take this a bit further. And so I did this with biotite and white mica because we had quite a lot of analyses of these to be able to look at variations with pressure and temperature and other variables. And so to answer this, I took all of my analyses, and the same as I did in the whole rock study, I just classified them into one of these zones. So this diagram looks complicated. It's pressure along the right axis, temperature down here, and then XFeD+. So the temperature axis is the same as the zones that I used in the whole rock study, increasing grade from chlorite, biotite to garnet, staurolite, sillimanite, and then K feldspar. The pressure axis is defined based on what we call the facies series, so cordierite, andalusite, low pressure rocks in the lowest pressure, staurolite, andalusite, sillimanite rocks in the middle area, and then staurolite, kyanite, sillimanite, Barovian type rocks at the highest pressure, and classified them into each one of those zones. And then because I didn't have a whole rock measured XFeD+ for every single analysis, I just looked at the literature and decided, well, does the author report the type of iron oxide that's present in the rock? And so I classified them again based on iron oxide. And this is the result. It looks complicated. Each of these is a mean with a standard deviation and a range. But in biotite, the general trends might be that, well, there's not much change with increasing temperature in the XFe3+ at the top or the iron 3+ cations in biotite. But I think, although it is within uncertainty, there's a general increase from no iron oxide through to hematite-bearing rocks in the XFe3+ of biotite. Iron 3+ cations is probably more complex. They all seem to have relatively similar mean values here at the bottom, and so maybe the number of iron 3+ cations stays the same, but you're changing the ratio of the iron 3 to iron 3. I think we need a bit more data to actually say something concrete about this, but this is what we have at the minute. And I did the same in white mica, which is even more all over the place, I would say. There's possibly a difference here between no iron oxide and ilmenite bearing rocks versus magnetite hematite, but it's all well within uncertainty. There's supposedly a decrease in the number of iron 3+ cations with temperature in muscovite, and then there's some oddities, like the ilmenite bearing number of iron 3+ cations is much lower. And so this shows the kind of caveat in this database in that there are a lot of ilmenite bearing samples that were done with Mossbauer, and Mossbauer is combined with probe work, and so some of the wet chemical analyses may have been overestimating the total iron because they probably have inclusions of perhaps the oxide minerals in there. So not perfect, but something at least. And then we picked out some correlations, so how well do the recent models that I talked about do in reproducing the XFE3+ of these minerals? So I'm modeling in Ferric domino, for anyone who cares. I'm using a full system MNNCKF MASH-TOW system with this latest data set because it has iron 3+N members for all of these different things. And I use an average database bulk composition to produce a PT diagram that looks like this. So the different colors on here, the grays, are the different oxides that are the major oxide in that field. So at the top it's hematite with ilmenite, at the bottom is magnetite with ilmenite. At the lighter the color, there is no iron oxide, and then there's a small ilmenite only field in the middle. And so at the same time I made a TX diagram to look at how the iron oxide varies with XFE3+, and we see that at the bottom there's no iron oxide at low temperatures, ilmenite, a zone with magnetite between 0.1 and 0.3, and then hematite at higher. So that mirrors what we observe in the rocks, in that at low XFE3+, you can see ilmenite, magnetite, or maybe even no iron oxide, and that hematite belongs to much higher XFE3+ values in whole rocks. So how well do the mineral compositions do? This happened last time. I should probably check this better. So this diagram here, the color represents the change in biotite XFE3+ with pressure and temperature. You can imagine if it's sat on top of this diagram, that's where biotite is stable. And so remember, biotite XFE3+ is about 10%, and this diagram predicts that it changes from 0.04 to 0.16, so 4 to 16%. We didn't see any change with pressure or temperature in the biotite number of XFE3+ or Fe3+ cations, so that's a little bit skew-off. And in terms of with XFE3+, so with increasing hollow rock XFE3+, we see that it changes from 0 to 0.5, and well, we saw it go from 0.08 to 0.18, even with a plus or minus 0.08 uncertainty on that. So there's something not quite right with the model's prediction of how it should change with whole rock XFE3+. And we can do the same for muscovite. Muscovite is about 54%. Here it goes from 0.15, 15% to 45%. So muscovite is underestimating the amount of XFE3+. And here we go from 0 to 1, whereas in our natural data it went within a plus or minus 0.15, probably 0.5 to 0.65. So there's a few things that probably need tweaking with the models to make these work, or to mirror the natural rocks better in the future. So did I answer these three questions? Well, I hope so. The first is that muscovite has the highest XFE3+ of all. Biotite, chlorite, and staurolite are similar, probably lower. Biotite seems to vary. The XFE3+ of biotite varies with XFE3+, but the iron 3+ cations are somewhat constant. Muscovite is a little more complicated, and I would say these need some improvement. And the reason they need improvement is because it's really important to understand that ratio of iron to magnesium, and so if we get the iron 3+ wrong, then you subsequently get the rest of the composition wrong. Okay, so I think I'm at about half an hour there, so I'll quickly move on to the last part of this presentation. So how do these databases of the amount of iron 2, iron 3 in minerals and what a whole rock composition actually help for my PT determination in natural settings? And so I'm just going to talk about the work that I did during my PhD here. This is a photo of a beaver dam crossing in southern Canada, and this is where I did my field work, and I'll talk about why it was so helpful for me to have these and why hopefully it's helpful for other people. This is the Whetstone Lake area in southeast Ontario. The orange belt here is the Grenville province, just north of Toronto, and this is where I was conducting this field work. we went out, made an isograd map on the right-hand side. We mapped 4 metamorphic zones based on similar to what had been seen in previous studies. We had 250 samples, nearly 200 thin sections, 50 samples with modal abundances, 33 with whole rock geochem, 42 analysed by IPMR, and I think it's one of the most thoroughly documented and analysed sequences in a study at least, which is great. And what I'm going to talk about is what became most interesting about this study, if it loads. And so the isograds here from right to left are staurolitin, kyanitin, and soliminitin. It's a Barovian type sequence. And what I'm most interested in is these kyanite and lower soliminite zones. And so there's this restricted range of metamorphic grade, possibly 50 degrees or more, and within this we see this wide range of bulk composition and mineral assemblages. So here's my AFM diagram with my orange circle showing the worldwide metapelites from the database, and each of these points represents a different rock that we analysed at Whetstone Lake. So you can see that Whetstone Lake is an area where the whole I've got an average pelite and everything should be the same doesn't hold, because it produces this wide range of bulk compositions. And so we have garnet bearing these red hexagons that are garnet staurolite biotite bearing rocks. I have garnet free kyanite bearing rocks that are really dark biotite rich with staurolite and kyanite and no garnet. We have cordierite bearing rocks that are blobby, bulbous and outcrop and kind of grey, that are muscovite and biotite, well, in average proportions. And then there's these muscovite rich rocks like that in the top left, these green squares, and they have a range of porphyroblasts but look very different. And so there's these very different looking rocks with different assemblages across the entire region. And the reason for that is this change in bulk composition. And so if we look at the iron 3+ again, this is an area where iron 3+ is really important. Here's my database on the left-hand side, and here's the range in the entirety of the rocks in these 2 zones of Whetstone Lake. They've spanned the entire range of what we see in the worldwide database. So it's a really interesting area. And what this made me think is that, well, this is a better way to test the models in some respects compared to the average pelite I was using to test the iron 2, iron 3 before. I can collect some really thorough data on individual rocks. I know that they all come from the same package, and therefore they all attained a similar PT condition. And so the model should be able, if I put in all of these different bulk compositions, to predict the same PT condition. And that's about as good a test, I think, as you can get. So I picked 2 garnet-bearing rocks, 2 kyanite-bearing rocks, 2 cordierite-bearing rocks, and 2 muscovite-rich rocks, and we took them to model. I had a couple of questions before I started modeling. First, what's an appropriate bulk composition? This is something that I think, well, the answer is kind of seems obvious to you, but I did both just in case. So people typically either use a whole rock bulk composition with XRF and compare their phase diagram made from that powder with what they observe in a thin section taken from a different portion of the rock. That's the left-hand side. Or they map the thin section or combine modes with representative mineral compositions and make a phase diagram based on that local bulk composition. And so I did both of these to try and determine, is one better? Do they come out with the same answer? Does it really matter? And the second question I had was, well, how do you assess how well a model is doing? What I'd done in the previous study, where I'd taken the average, I was just looking broadly, does the X epithelius match with something else? But in these rocks, I wanted to try and assess how good is the mineral assemblage predicted, how well are the modal abundances predicted, and how well are the mineral compositions predicted. And if there are consistent discrepancies, can we use those to help refine the models in the future? And so what I decided to use was these quality factors from Eric Dusterhoft and Pierre Lenari's 2020 paper. And this is just a method for me to quantitatively analyze the goodness of fit between the prediction from the model and the observation. And I think this is the first application of this, or there's probably others, but to really help refine what's wrong with the models. And so there's 3 levels of examination, the same 3 as I said before. There's QASM, which is the assemblage, Q volume, and QCMP that have these equations to rate the relative fit between the prediction and observation that I won't get into. I'll just tell you that's what they are. So this diagram on the left shows you for the whole rock bulk compositions for 8 samples, the predicted assemblage fields outline, and the dots represent where I picked a PT point within that field. So overall, this is quite good. I've modeled 8 samples with 8 different bulk compositions, and all of the fields somewhat overlap. So that's somewhat reassuring that I can get a similar PT condition 6 to 8 kilobars, ignoring perhaps the C3 at the bottom that's a little bit off for reasons I won't get into, and a 50 degree C between all of them. I think that's quite a good result, and we can do the same with the local bulk composition and get relatively similar overlapping fields between these. But we use the quality factors to go a step further than that. This looks like a complex graph. It's a 3D bar chart, so the y-axis here is the quality factor out of 100%. The 3 bars are, the back bar is the assemblage quality factor, the middle is the modal abundance, and the front one is the compositions. And then my samples are listed along the bottom. And so the brown represents the XRF bulk comp, and the turquoise represents the MADE, or the local bulk composition. And so we can talk through this. The back is always close to 100%. So I can always find an assemblage on my diagram that matches what I see in my rock, which is why I can end up with all these things overlapping in PT space. The modal abundances, well, they vary between maybe 70 and 90%, but you'll notice that the turquoise bars in the row second in from the back are always higher than the brown. And so what that means is that making a local bulk composition, you're more likely to match your modes than you are with an XRF, which makes total sense, because if you put the modes into the model, you would hope that it then pulls out the same modes. But it's an important point that if you're modeling with an XRF bulk composition, maybe using modal abundances isn't the greatest way to constrain where you are on the diagram. And then the closest row of bars, that's the composition. And so the composition varies between, well, I think it's 20% and 50%. It's always really low. And that frustrated me and was something I wanted to figure out, why was the QASM so poor? And so I went in and made these 1-to-1 plots. The observed number of cations is on the left. That's what I see in the rock. And the observed is on the x-axis, and the number calculated by the model is on the y-axis. And so we see that silicon is underestimated in biotite here. Titanium is always overestimated in biotite and staurolite. Aluminium is overestimated in muscovite, and XMG is overestimated, and this is perhaps the most worrying, in garnet, staurolite, and cordierite, which we use often for thermobarimetry. So there's consistent discrepancies through the models, and that hopefully that means that it's something in the back behind the models of what they've chosen for a parameter that means that it's always skewing it in one direction that can be in the future fixed as a result of what we've seen here. And to say, well, why does this matter? Well, this diagram on the right that we use to take our assemblage out of, that is totally and utterly dependent on the mass balance between the different compositions of the minerals and how the modal abundances of those interact. And so you wonder, if all of these compositions were much better predicted, how much would these lines, or some of the lines on these diagrams, move, and would it change our PT estimates? I don't have the answer to that. I'm still working on that. I think the answer is in some cases yes, in other cases perhaps not, but I think it's something we need to strive to get better in the future. So with that, I'll just give some conclusions. I hope that this work provides some insight into problems that metamorphic petrologists looking at P-lights worldwide find useful. The main conclusions are that meta-P-lights have a broadly similar composition, but variation can exist, and it does lead to differences in mineral assemblages and compositions. Apart from the loss of volatiles and the reduction of iron to the biotite zone, metamorphism appears to be somewhat broadly isochemical. Iron 3+ can be significant in metapelitic rocks and minerals, and hopefully these databases can be used to give people an answer to that. And current thermodynamic modeling does a poor job of matching mineral compositions in pelitic rocks. And I think detailed natural data sets, whether they're databases or whether they're individual samples that have been really well studied, they're only going to help refine these future iterations of thermodynamic models. And with that, I'll leave this slide up. This is some pictures of some of the giants, I think, in petrology. If you've not heard of some of them, go and Google them. They all did excellent wet chemical work in the 50s, 60s, and 70s. Yeah, we can talk about them. But that's it, and I will take any questions. Sorry if that was too quick. I know my accent's not the easiest to understand.
Okay. I have a few questions, but don't want to focus more on my question. So there is something interesting about P-lights. In one of the regions I work in Brazil, that's the Carrancas region.
Okay.
We can follow from low grade to the beginning of amphibolite fascists until middle of amphibolite fascists. And when we start amphibolite fascists, the P-lights, we can still see the layering of the sedimentary rocks.
Yeah.
So it's quite difficult to establish what is the bulk composition, because sometimes the sunlight won't grill in some of the very tiny layers.
Yeah.
So what is the bulk composition that we should choose to do a pseudo-section?
Yeah.
But when you follow the same unit to a higher temperature, the layering disappears. So the deformation metamorphism destroy the layering.
Yeah.
And then you have kind of a more uniform bulk composition. And this is good because metamorphism make the job for us.
Yeah.
So how to really control this kind of stuff in kind of a low-grade rocks when we really cannot determine what is the very small, tiny bulk composition, when this really makes a difference that the chloritoid or starlight is going to just grow in a very tiny composition. Sometimes we really need to determine like molds or use microprobe instead, really crush the rock.
Yeah, I think that's an excellent point, and that is, I think, what I came to conclusion in that to compare an XRF from a piece of rock that you've not looked at and just crushed to your thin section probably isn't the best way to go about this, in that studies have shown that whatever area of the thin section you map and input into your model, you should be able to reproduce. I think there's some work by Pierre and Eric in one of their papers where they took a thin section, mapped the entire thing, and then randomly chose separate parts. They chose the aluminous layers, they chose the quartz-rich layers, and whatever they put in, the model reproduced at a similar pressure temperature condition, no matter what the bulk composition was. And so I think that just mapping in general is probably a safer bet, especially in those more complex, lower grade rocks. Then we have to think about the idea of, well, is there actual equilibration if you're looking at these small layers that are aluminium rich with the staurolites and combining that in with everything? What is the length scale of equilibration, and is it appropriate to model that all as one? And that's a hard question that I don't think anyone has the definitive answer to, otherwise we'd be doing it. And the answer is probably that disequilibrium is pervasive in low-grade rocks, as anyone who maps before the porphyroblast comes in, the compositions in chlorite and muscovite, they vary quite significantly across thin sections. So, I hope that answers your question.
Yeah. I have another one.
Of course.
How well do you think we can really measure iron 3 in rocks?
In rocks, yeah. So the caveat is that I say 10 to 30%, but I think that's an overestimate. The biggest problem I had at Whetstone Lake is that I sent off all of my whole rock and I got titrations alongside it. But the titrations were far above what I expected, because I think the rocks were all oxidized to some extent during the crushing process, as you might expect. And so if I compared my local bulk comp, the modes, where I took a modal abundance, I combined the biotite with my estimate of 10% and the muscovite with my estimate of 50%, all of that together, I get a number of, 8% of the iron in the rock is iron 3+, and yet the titration came back as 22. And so I worry that these estimates from titration should probably be taken as a maximum, and again, that this mapping approach might be better. But in rocks, I don't know how well. I think we'd be better doing in situ measurements in minerals and combining that with modal abundances to have an understanding of that. And that's not something that's new. There's papers written 50 years ago that crushing probably oxidizes your rock. There's problems with porphyroblasts not dissolving in the chemicals they use to do the titration, that these papers have 10 or 15 citations and nobody's ever really looked at. There's some work in xenoliths from the late 90s, I think Dante Keneal, and he talks about, actually he thinks there's lots of sludge along the grain boundaries, and that's probably full of iron 3+, so they don't get the right answer when they do a titration. So I think we probably can't measure it very well in whole rocks, and I would argue for analysing it in minerals.
And in tropical countries like that.
Yeah, of course, yeah. Here, I'm sure it's even more of a problem than it is in Canada, where it's, nice and dry sometimes. Yeah. Hey.
Sorry. It's already hard to differentiate wax from mud rocks with rocks with no metamorphism. And when you get low grade or high grade, it's getting worse. Then what about the presence of iron-rich lithic fragments in these kind of wax and mud rocks? Then you call pellets in the end. So you did put in the balance for the iron the possibility of iron-rich lithic fragments inside of those rocks.
As in the original deposition process, you have these fragments of that are rich in iron.
Yes, from the protolith.
Yeah, and so I'm sure if we looked at them at low grade, you'd observe those from a sedimentary point of view. But with increasing metamorphism and deformation, well, maybe in certain P-lights you would observe that they're left over and relict, but I assume they're homogenized in if you get up to the amphibolite facies. I think there's a entire thing that I'll admit I don't have the background or understanding for in the sedimentary side, that there's this incredible variation in P-lights that us at metaphysiologists don't really consider how that occurs in the first place, and what occurs as part of deposition, what occurs as part of diagenesis, what occurs if there is any mass movement during metamorphism. Does that answer your question? Or, yeah. I'm sure there's a role for that. All right. Cool.
And just curiosity, in your paper in geology, did you differentiate carbon-rich pelites from another one?
Yeah, so when I had that database of 6,000, we made 4 coals. The calcium had to be less than 4 weight%, because otherwise you end up with a load of calcareous P-lights. And we kind of plotted them, and you can see them. You had to have more potassium than sodium, so we don't include weird meta-grey wackies that are kind of more feldspar-rich original sediments. Aluminium had to be greater than 12 weight%. And there is one other coal that is, I've forgotten now, but it's in there somewhere, and we talk about how we pick these filters and why we pick them, and to get down to just the P-lights at the end, because there's variation beyond just what we call P-lights into semi-P-lights, grey wackies, etc., etc.
Yeah.
Yeah.
Thank you.
Yeah.
James, thank you for presentation. Do you think that we have the same problem regarding the coupling with mafic rocks too, between thermodynamic database and iron 3 in original rocks?
As in the same problem in the natural rocks and in the models?
For mafic rocks.
Yeah, I mean, iron 3+ is always the problem, because we can't measure it, and we don't measure it in situ. And I think from the little work I've done, and I'd love to do it, but I'm not ready to take on a database project right now, whole rock geochemical analyses from metabasites also show the variation in XFE3+ that we see here, and there are examples. There's really good stuff in, I think, the Ryoki belt in Japan from the early 80s, of looking at the differences in hematite bearing and ilmenite bearing metabasites and how they vary in the assemblages upgrade. And so I think the exact same problem exists there. The nice thing about metabasites is that they're a simpler system, in that you have plagioclase amphibole, at least at the amphibolite facies. Epidote, you'll probably assume that all the iron is iron 3+. Garnet we can estimate. Orthoperoxine and clinoperoxine, it's low, but we can somewhat estimate. And so the only thing we have to worry about is amphibole. And the estimates in there are not great, but we can at least have a way to estimate it based on stoichiometry. So I think it's the same problem, but I think maybe that's just my perspective. I think it's more complex than the pelites because you have these phyllosilicates with multiple vacant sites that then means estimating iron 3+ effectively, other than just putting an estimate in like I did, it isn't possible from a stoichiometric point of view.
If it's just amphibole, that's the problem. It's easy.
Yeah, yeah. But I mean, the best thing is you read there's the Hawthorne volume for amphiboles, and they have this appendix on how to calculate iron 3+, and they write in there, we compared the wet chemical analyses of iron 3+ and amphibole, took all the iron, made it iron 2, and then put it through their estimation, and they don't line up whatsoever. And so the estimation doesn't really, well, unless you think that the measurements are wrong, the estimation isn't amazing either. But you have to estimate something, because if you assume it's all iron 2+, that's also an estimation.
Yeah.
You know, you're saying that it's 0, and so I think you're better to at least put something in, talk about the uncertainties on that, than you are to leave it to. So, yeah.
Yeah. Thank you.
Great.
Any questions?
Cool.
So, thank you
Thank you,
very
everybody.
much.
That was great.